Hi everyone, this is lesson number 8 on the statistical methods in high-energy physics. In this video, we will talk about the method of maximum likelihood. There will be a lot of derivatives in this video. We suggest you quickly recall your skills from the kindergarten, or you will get lost otherwise. This video is about finding maxima. And whenever somebody says maximum, we should immediately say derivative. What are we going to maximize? Our chance to win the lottery? No, something much better. We are going to maximize our chances to find a good parameter estimator. Yes, if an efficient estimator of a parameter exists, then the method of maximum likelihood will find it. It's worth giving it a try, isn't it? First thing to make clear, likelihood is not the same thing as probability. Well, just in statistics. Please don't correct people on the street when they say likelihood. Otherwise, you just maximize your probability to look like a nerd. However, in statistics, probability and likelihood are not synonymous. Probability distribution is a function of set of random variables, or data if you like, and it is parameterized by a bunch of parameters. In a measurement, in fact, we sample one data point from this probability density function. A likelihood function is this probability density function evaluated at the measured data point. It's what you get if you plug concrete measured data into your probability density function. Therefore, we view likelihood as a function of the parameters, but not of the data. So the likelihood function is written as L of theta vector equals to f of x vector observed with parameter theta vector, where x vector observed is our measured data. This x vector observed can be anything we measure in our experiment, from a single count of events of a certain type to a huge sample of millions of values of reconstructed invariant mass. Please be aware that sometimes people use the word likelihood also for the full probability density function, before the measured data are plugged in. For these people, likelihood is therefore identical to the probability density function. L of x vector with parameter theta is equal to f of x vector with parameter theta. However, in this video, we will not use this terminology. Let's have a close look at how the method of maximum likelihood works. The first ingredient we need is the probability density function for our measured data. This probability density function is sometimes called the statistical model because it models how we think our data should look like if we knew the values of the parameters. On the previous screen, we have called it f of x vector theta vector, but let's use a different symbol because I want to reserve f for something else. So our statistical model can, for instance, be denoted as g of x vector theta vector. To get the likelihood, we just need to plug in our concrete measured data, as we have said earlier. A very common situation in particle physics is that we measure a single observable, or a small number of observables, but we measure it independently many times under identical conditions. In this case, all the measured values are sampled from the same probability density function. Our data is then equal to a set of n measured values, xi observed, each sampled from the same probability density function, f of x theta vector. We can view this set as one vector in n-dimensional space, x vector observed, and we can ask about a corresponding probability density function, g of x vector with parameter theta vector. Given the independence of the measurement repetitions, it's clear that the joint probability density function for the whole set is just a product of probability density functions for individual measurements. G of x vector with parameter theta vector, which equals to f joint of x vector with parameter theta vector, equals to a product for I equals to 1 to n of f of xi with parameter theta vector. While this is a very common statistical model in particle physics, note that our data does not always have to be an outcome of repeated independent measurements, or at least not directly. The simplest example one can imagine is so-called cut-and-count experiment. In this case, we try to estimate the cross-section of our studied signal process just by measuring the number of events that pass some selection. Our observable is therefore just one variable, the number of observed data events n, and the statistical model for this measurement is just a simple Poisson distribution. G of n with parameter sigma signal equals to L times sigma signal plus sigma background all to the power of n over n factorial times exponential of minus L times sigma signal plus sigma background. Here, the luminosity L and the background cross-section sigma background are assumed known, so the probability density function has just one parameter, cross-section of the signal. Another example is so-called least square fit, where the statistical model is a product of not identical Gaussian distributions. We will talk about this method later. Regardless what our statistical model is, we always get the likelihood function by plugging the observed data into the model PDF, and the subsequent treatment of the likelihood function is always the same. Therefore, we will explain the method of maximum likelihood using the textbook example of joint probability density function for repeated experiments. If we evaluate the joint probability density function at the observed set of measured values xi obs, we are getting the likelihood function. L of theta vector equals to product for I equals to 1 to n of f of xi obs with parameter theta vector. As said already, the likelihood can be formally treated as a function of the parameter theta vector. The maximum likelihood estimator of the parameter theta vector are the values that maximize the likelihood. L of theta hat equals to max over theta of L theta. Let's show the motivation for this choice of the estimator now. Imagine that you are measuring the speed of Cristiano Ronaldo's shots. You kindly ask him to stay 2 hours on the pitch with you and to shoot n times in an identical way. Each time you measure the speed of the ball with the same detector. Let's draw each measured value of the ball velocity as a line on the x-axis. Effectively, each shot means that we are sampling one value from the probability density function f of x with parameter theta. In order to make the maximum likelihood estimate, we need to know what this PDF is. But for simplicity, let's just assume it has the shape of a hill and that the parameter theta is its mean value. As you do the measurement, many shots are accumulating around the mean value of this probability density function. But there are also rare situations when the speed is very high or very low. Even Cristiano Ronaldo can kick the grass instead of the ball occasionally. When you finally let Cristiano leave and take a shower, we can start estimating his theta from the precious data. We take possible values of Cristiano's theta, one after the other, and for each value we calculate the likelihood of the whole dataset. When we try the value of theta that is very far from the actual true value, the likelihood will be very low, because it is a product of the PDFs evaluated at points where the probability density is very low. As we get closer to the true value of theta, more of the measured data points will end up in the region of the probability density function with higher probability density. It's clear that closer we get to the true value of theta, the higher likelihoods we get, because our data is mostly clustered around the true value. Therefore, we choose the value for which we get the maximum likelihood as our estimate of Cristiano's theta. From what we've just said, it might look like that the estimated value is identical to the true value of theta, but it is rarely the case. One has to realize that because our measured sample has the finite size, this estimated value of theta will suffer from statistical fluctuations. So the estimate of the theta would be close, but will not be identical to the true value. When you are done, you meet Cristiano in front of the football stadium, and you tell him that his theta is 100 kilometers per hour. He immediately asks you to show him how this maximum likelihood estimator was mathematically derived. So let's do it then. We take the joint probability density function defined previously and insert our measured dataset. This gives us the likelihood function that we formally regard as a function of theta. We find the position of the likelihood maximum with the use of a derivative. d of L of theta by d theta, evaluated at theta equals to theta hat, must be equal to 0. The position of the maximum is our estimator of theta. In practice, we don't use the likelihood function as it is, but we rather use its natural logarithm. Logarithm is a monotonic function, and therefore the position of the maximum does not change if we take a logarithm instead of the function itself. Logarithm changes the product of a huge number of terms into a sum, and the sum is much easier to work with than a product. Moreover, people typically use a negative log likelihood and search for its minimum. Of course, the function minus log L theta equals to minus sum of I from 1 to n of log L theta has minimum at the same place as the likelihood function's maximum. Let's have a rest for a short moment, and what's better for relaxation than a nice calculus problem? We will demonstrate the maximum likelihood method in action. For this, we assume that we sample n values from a normal distribution, and we want to estimate its mean value mu and standard deviation sigma. The joint probability density function for a dataset like ours is f joint of x vector with parameters mu and sigma equals to product for I going from 1 to n of normal distribution of xi with parameters mu and sigma. The log likelihood function is log of L of mu sigma equals to sum for I going from 1 to n of 1/2 of log of 1 over sigma squared minus xi minus mu squared over 2 sigma squared plus log of 1 over square root of 2 pi. Requirement of the likelihood maximum yields two equations for two unknown variables, mu hat and sigma hat. Let's start with the equation for mu hat. Derivative of log L by d mu equals to minus of sum for I going from 1 to n of d by d mu of xi minus mu squared over 2 sigma squared and this equals to sum for I going from 1 to n of xi minus mu over sigma squared for mu evaluated at mu hat, and this must be equal to 0. The last equality implies the equation as simple as this. Sum for I going from 1 to n of mu hat is equal to sum for I going from 1 to n of xi. Therefore, the maximum likelihood estimator of the mean value of a normal distribution is an arithmetic mean of the measured data values. Mu hat equals to 1 over n of sum for I going from 1 to n of xi, which equals to x bar. Let's look at the derivative with respect to sigma now. D log L by d sigma equals to sum for I going from 1 to n of 1/2 d by d sigma of log of 1 over sigma squared minus d by d sigma of xi minus mu squared over 2 sigma squared. And this equals to sum for I going from 1 to n of minus 1 over sigma plus xi minus mu squared over sigma cubed this evaluated at sigma equals to sigma hat, and this must be equal to 0. The last equality is obviously a very simple equation. Sum for I going from 1 to n of sigma hat squared equals the sum for I going from 1 to n of xi minus mu squared. Thus, we are getting the well-known formula. Sigma hat equals to square root of 1 over n sum for I going from 1 to n of xi minus mu squared. Note that we haven't inserted the mean value estimator to this formula yet. Actually, there might be situations in which we know the true value of mu. If we don't know it, then we use the estimator instead. In summary, the maximum likelihood estimator for the normal distribution parameters are the notoriously known formulae that we must put in the golden box once again. Mu hat equals to x bar, and sigma hat equals to square root of 1 over n times sum of for I going from 1 to n of xi minus x bar squared. They correspond to generic estimators of mean value and standard deviation that we investigated in the previous videos. Let's stress that the estimator of sigma is biased. In the previous video, we've shown, however, that the bias can be calculated and corrected for. In the calculation we have just made, we didn't estimate the variance, but rather the standard deviation. Given that the variance can be viewed as the normal distribution parameter as well, we could have estimated it by deriving the log likelihood function with respect to sigma squared instead of sigma. However, there is a more general and very easy way how to get the maximum likelihood estimators for functions of parameters estimated with the maximum likelihood method. Let's take a generic invertible function a of theta of a parameter theta. If a derivative of theta by dA is not zero, then the maximum likelihood estimator of A is equal to the function A evaluated at the maximum likelihood estimator of theta. A hat equals to A of theta hat. This is absolutely wonderful, isn't it? Moreover, the proof can't be simpler. Let's just write it down. dl by dA equals to dl by d theta times d theta by dA. Given that the derivative of L with respect to theta is zero if evaluated at the estimator of theta, it follows that dl by dA evaluated at A equals to A of theta hat also equals to 0.